All right. So the stream should be on right now. I'm just checking out. Yep, it is on. All right, so I'm going to get started with today's lecture. Obviously, we got a few people missing, but one person said he has a flat tire, so he won't be here. But I'm not sure about the rest of the class. All right, so I'm going to start with something that I normally do not do, but I think this is kind of important. When you watch a lot of TV series, like at the very beginning, they will say, previously, dot, 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 right? That's what I'm doing. Okay, I apologize. I'm not using the right speaker. So let me fix that first. Alrighty. Well, it is supposed to be using the right speaker, but it's not. All right, there we go. And might as well check the recording, make sure it's using the right one. So the recording is using the right one, it's just that the x itself is a 1 or a 0, y itself is a 1 or 0 because they're binary now. We still have the addition here, and we still have addition here. And look at this is ugly because it's a mod, which implies a division. So next time on Thursday, we'll take a look at what happens when the tens turn into twos, and you go like, oh, so that is really cool. Because it is really cool, because when you turn the 10 into twos, you can actually use logical operators to get everything done. All right, so that's where we left off on Tuesday. And what we'll do today is to answer some of those questions, to address some of those points that I kind of brought up on Tuesday. So this is something that I need to do because I'm teaching two sections of the same class, and it's hard for me to kind of keep track of exactly where I left off for each class because it's hard to synchronize the two classes down to the minute. All right, so we're gonna close this tab, and I'm gonna switch to Joplin. So I'm not sure how many of you are starting to look into Joplin. Even if you don't plan to type in Joplin at all by yourself, it would still be helpful to install Joplin because then I can copy and paste, make a file, upload it onto Canvas of what is on this side. Then you can render it, on your side. You can print it out. You can export it to HTML, PDF, whatever you want to do. All right, so I'm just going to focus on the left-hand side because the right-hand side is what I type. The left-hand side is what you should be seeing. So read the modules and take notes of notations. Concentrating the notations and definitions can be helpful. This is something I've been trying to tell you guys since the beginning of the entire class. Okay, so all the definitions, all the symbols, all the notations, put it in one place of your own notes. Okay, if you're doing it electronically, it's super easy because you can always just insert additional items. If you're putting this on a piece of paper, then you have one piece of paper that should contain all the definitions, all the notations. The idea is you want those things to be easy to find, okay? Especially during the exam, you don't want to be scrambling to find the definitions. All right, second thing is sign into Canvas on the computer. You can use the computer in the lab, or you can bring your own mobile device, be it a laptop computer or a cell phone or a tablet, because we're just getting ready for road taking. Okay, I'm not doing that just yet, but you have some time to get ready for that. On the other day, I did write down the proof, kind of like an unofficial proof. This one is official. So if anyone is interested, I can basically just copy and paste this. Y addition can be replaced by or when we're computing k subscript I plus 1. And this is a complete proof, meaning that I even have a corollary to help me, to do the actual proof by induction. It is not, we are not going to, I will not ask you to prove in any homework assignment, in any lab, or in any exam. So some of you, if you think this is something that is definitely not something that you're interested in, you can ignore that, okay? It is not going to be tested on in this particular class. But I can assure you, in your future, near future, when you move on to a 4-year university, and depending on when you're transferring, it can be in a year, it can also be in about a month, in a few months. At a 4-year university, proofs are going to be important. So, if you have already taken CISP 440, you should be able to follow the proof, that is outlined here. Once again, it is not a main thing for this particular class. I have to do it because I need to know that I can actually prove that as a theorem. It is important to me. Doesn't mean that it has to be important to you, but if you're interested in that sort of stuff, that's going to be helpful. So what we'll do today for the rest of today's class, we are going to look into binary addition to continue with the discussion from Tuesday, so that we basically generalize our addition to any base, and then we specialize to base 2, and then we'll start to observe some kind of interesting stuff about base 2 with regard to the R function as well as the C function. So that's what we're going to do today. So are there any questions before I continue with the lecture? No questions? So is this helpful? Just kind of give you an outline of what we're going to be doing today and how it relates to the previous class? Okay, all right. I would imagine it's particularly useful next Tuesday after the long weekend. All right. So let's go back to the notes, okay? So once again, it is really important to read the notes and not just to kind of glance through it, okay? I'm talking about like reading sentence by sentence, word by word, noting anything that you're not quite understanding, and looking up those definitions and trying to understand it, to your best ability. If you still cannot make out, what it means, maybe it's time to contact me, okay, so that I can try to explain that to you, either in class or, in my office hour. My office hour is right before this class, so it makes it kind of convenient. You just have to come to campus a little bit early, go to my office. If I'm not in my office, I'm in this classroom because I need some time to set up everything. All right, so getting back to the definition of the C function and the R function, if anyone is still thinking, but what is the C function and what is the R function? I strongly suggest those people to really study, okay, because we have been talking about this for at least one entire class already. But the bottom line is, if you want to apply the C, which is the carry, part of the carry function, and the R, which is the single digit sum function, and you want to apply that not to base 10, but to base 2, it's easy. Change the 10 to a 2, and we're done. So are we okay with that concept? That's actually in the video replay that I did a little bit earlier. So assuming that we did that, okay, what I'll do is I'm going to copy and paste these, change the definition to specialize to base 2, and then we'll go ahead and see what is going to happen when we specialize in base 2. So I'm just going to continue my notes here. Converting from base 10 to base 2. So I'm typing some notes here, but do not let me take all the notes. So if you have something that you are thinking about, that you think, oh, this may be important, write that down, okay? So you should be taking your own notes as well if you think, oh, that's going to help me. All right, so all I'm doing here is I'm changing the 10 to a 2. So now we have C and R specialized for base 2. Now, in base 10, it's pretty long, okay? When you look up the single digit, or if you just want to figure out what is 6 plus 7 or 6 plus 8, it takes elementary school students probably a week or so just to understand the concept, and then maybe another 2 weeks or so to remember, okay, to memorize that 6 plus 8 is 14, because it's not easy for us to actually understand that stuff. It is all memorization. In base 2, on the other hand, is super duper easy. So the way we look at this is to think of this as a table. So I'm going to make a table in Markdown. So we got x and y as independent variables, and then we want to figure out what is c of xy, and then we want to figure out what is r of xy in base 2. So I want to show you the functions also, just so that we know what functions we are talking about. And then we'll go ahead and fill up this table so that we can figure out what it looks like in base 2. All right, so x can be 0, y can be 0. And I'm just going to leave this part blank for the time being. And then we have 0, 1. And then once again, leaving those two columns blank. And then we have 1, 0, leaving everything blank. And then finally, we have 1, 1, and then leaving everything blank. So there we go. Now, if I were to make this table for base 10, it's not going to be 4 items, right? How long is this going to look if we're talking about base 10? In base 10, x can range from 0 to 9, and so can y. So how many rows will we be talking about in base 10? Yes? 100. 100, very good. Don't you think 4 is quite a bit less than 100? I like this. Much better than base 10. All right, so now we apply the actual function and try to figure out what is c of 0, 0. So you guys can just focus on the actual definition of c in base 2. So what is c of 0, 0? X is 0, y is 0. So just carry out the statement or the expression. We have 0 plus 0 greater than or equal to 2. If it is, we return a 1. If it is not, we return a 0. So what would be the answer to c of 0, 0? All right, you guys know the answer. You just have to let me know. 0, very good. And what about c of 0, 1? 0 plus 1 is 1. 1 is greater than or equal to 2 is false, and therefore another 0 here. This is symmetric because x and y are just added, and addition is commutative, which means if you flip the order, everything is going to be the same. And this is the only one that looks kind of interesting, because if x is 1, y is 1, then x plus y, 1 plus 1 is exactly 2. 2 is greater than or equal to 2 is true, and as a result, we return a 1 over here. So if you go to the r function, okay, we want to figure out what is the r of 0, 0. So if you look at the function itself, 0 plus 0 is 0. 0 mod 2 is 0. Yes, exactly. And then we have basically 1 mod 2 is 1. 1 mod 2 is 1. 2 mod 2 is 0 again. Are we okay in terms of understanding why c of xy and r of xy have these values filled in? Is that okay? All right, because all that is really just running those functions with the respective value of x and the respective value of x and y, and then we just compute the whole thing, find out what is the return value. So we look at this, and we find out that both c xy and r of xy, they only give you zeros and ones. Now, the c function giving you a result of 0 or 1, we kind of know that that's going to happen. Okay, that's not a big deal. But r is giving you also zeros and ones as results. So that seems kind of encouraging, because if you see only zeros and ones, that means maybe we can do this with some kind of Boolean or logical operators. If you start to see like 2, 3, 4, 5, and so on, probably not, right? Because those are values that are not just true and false. But in this case, if you look at 0 as false and 1 as true, maybe, just maybe, we can use a Boolean expression instead of actual addition and comparison and all that stuff. So we're going to focus on the easy one first. The easy one is the carry function. So if you look at the carry function, can you imagine a binary or logical operator that would give us exactly the same result if we plug in the x and the y. So let's call the operator blah, okay? So x0 blah 0 is going to be 0, 0 blah 1 is 0, 1 blah 0 is 0, 1 blah 1 is a 1. So does it remind you of any Boolean operator that can get exactly the same job done? And, all right, logical and. Okay, very good. So if I were to change or extend the definition of C of xy and say, just for binary, I am going to use this to compute C of xy, it's going to be okay, because it's the same for every single row in the table. Any questions? No questions? Okay. What about R of xy? Now, R of xy is a little bit more complicated, because if you look at this, unless you look at the last row, you go like, oh, cool, because logical OR can get this done too, except the last row doesn't work with logical OR. Yes?
Is it not AND?
No, NAND doesn't work either, because NAND is going to be 1, 1, 1, 0. So you're missing just one row also. Yes?
Is it exclusive OR?
It is exclusive OR. Okay, so it is exclusive OR. So we can now say, oh, okay, this is just X exclusive OR with Y. In C and C++, there is no logical exclusive OR operator. So that's the best way I can do it, is to spell it out as XOR. It can also be known as EOR, because exclusive starts with an E, but most people start with an X for the exclusive OR. So it can be EOR or XOR. There's no specific operator to do that. All right, so are we doing okay so far? Now, how do we know this is matching exclusive OR? All you have to do is to Google search for the truth table of exclusive OR and then match what we have originally for R of xy to the truth table of exclusive OR, and you will find that they are an exact match, okay? And that's why we can verify that this is going to work. But there's only one problem. The one problem that we have is I want to reduce everything to the point where we can use transistors to implement everything, because that was kind of the whole point of why I started this entire semester talking about 2 p transistors and 2 n transistors to make a NAND gate. So now we look at exclusive OR and go like, I mean, it's nice that we can use a single operator to mean that, but can we actually use the operators that we are familiar with, which is negation, conjunction, and disjunction, to do exactly the same thing? Well, as it turns out, yes, we can. It just looks a little bit ugly. So I'm going to introduce the ugly expression, and it's going to be not x and y, or, okay, I need a backslash here to escape it, or x and not y. There we go. So exclusive OR really is just a nifty term. Instead of you having to have this messy expression here, you can now say, oh, exclusive OR. It's a shorthand, it's kind of handy, but at the end of the day, they are equivalent. Now, if you remember, I always keep asking you guys, how do you know that is true? Well, I'm going to leave this one up to you. Okay. In other words, you want to substitute the x, y value into this really kind of long and kind of clumsy expression and verify for yourself that it will give you exactly the same results as R of xy, and also going to give you the same result as x exclusive OR with y. So I'm not going to do it in class because it's going to take up a little bit of time, but I want you guys to practice doing it so that you can convince yourself that it is equivalent. Yes?
Where would we be able to access all this that you're writing down here?
At the end of the day, if you remind me, it's all saved anyway. But at the end of the day, if you remind me, I can give you the markdown version, which is on what is on the left-hand side. So as long as you install Joplin on your side, you just paste it into Joplin, and you can get the right-hand side. At which point you can now export it to PDF, export it as HTML, do whatever you want with it. Yes, sir.
Wait, so I actually haven't seen that. Like, exclusive OR? Like I've seen it in 370, I think, but is that an actual operator in
Not in
C++?
C or C++.
Okay.
Yep, not in C or C++. In Visual Basic, maybe, I'm not really sure. Um,
I think it was.
It may not be called exclusive OR either. Visual Basic has really weird names for the operators. But anyway, in this class, that's how we can, make this happen. So what is the big deal at this point of time? Yep.
Because we know how to make both an and a not operator
Mm-hmm.
and an or operator using NAND gates.
Yep.
Which means we can just make this in Logisim.
Right, exactly. So that means, this can be done in Logisim using, transistors, right? We can boil everything down to transistors. So can this thing, okay? Yes, it's gonna take a lot of transistors. But the point is, it can be done using transistors. That's all I want, okay? I'm not, going after optimization. I'm going after possibility. Can we do this? And the answer is, yes, we can. And that's not a political slogan in this class. So now, what is the big deal? Because this eventually is implementing an OR function that looked like that before. This, in return, is implementing the C function that looked like that before. But they're equivalent. So that means I no longer need to do something like this. I can now take this thing and say, oh, okay, we don't need to use addition and comparison and that sort of stuff. We can just say x and y over here, and then over here, I'm getting lazy. I'm just going to copy and paste. So we'll copy this entire thing, paste it, and then remove the backslash because that's also unnecessary. Or I should say, it's incorrect to use a backslash in that case. So now C is done using a logic gate. So is R. It can also be done using logic gates. All right. So last time there was one last thing that was bugging us. And I kind of talked about it, but I did not really give you the proof. Earlier in today's class, I basically said, yeah, we can prove it, but it's kind of tedious, and you're not going to be asked, how to do that. So I'm not going to focus too much on that one. I'm looking for K of I plus 1, the definition. So let me go. Sorry about all the scrolling, because I know it can be nauseating from your perspective. There we go. So I'm talking about this statement here, okay, the third line or the third bullet point. So see that plus here? That really is addition, okay? But addition is not good. It is not good because I can't do that, or I don't know yet how to do that using transistors, right? So it'd be nice if I can get rid of the addition and replace it with a logical operator. Then I'm all set because I know how to change any logical operator into transistors. Because at that point, okay, at this point in time, in phase 2, I know how to do the C function using a logical AND. So these two sides are now done, okay? I can use the logic gates to do both of those. But the plus is the problem because I don't know how to do arithmetic operations in logic gates. So that means I'm going back to my notes here, and just the earlier part of that. Some of you missed this discussion because I talked about this before the class, and some of you arrived a little bit after the class started. So this proof, the whole thing, boils down to this thing here. The whole thing boils down to the fact that K of I plus 1, you can do an arithmetic operation of addition, but at the same time, you can also replace the addition using a logical OR. The reason why you can do that is because in this very specific context, C of xi, yi, if it is a 1, it guarantees that C of qi, ki has to be a 0. And vice versa. In other words, if C of qi, ki is a 1, it guarantees that C of xi, yi has to be a 0. How do we know that? That's all the proof stuff that I was doing before. So all the stuff, from this point and all the way to the beginning over here, that is the proof. If this is the first time you see a proof like this, because you have not taken CISP 440, you can kind of glance through it if you're interested, or if you're not interested, you can just kind of forget it. Okay, you don't have to do a single thing about it. On the other hand, if you have taken CISP 440, you should be able to follow the logic. Okay, so this would be a good test to see if you are understanding and retaining all that stuff from CISP 440. Let me ask you this question. Why do you think it is important to understand and retain what you already, if you have already taken CISP 440? Because here, we don't have any other classes. There are no classes here that depend on CISP 440. It is a capstone class. It is the last class that you need to take, in terms of the dependency. So why would it be important for you to still retain and understand those concepts?
Otherwise, there'd be no use in taking it.
Well, yeah, but okay. So let me rephrase the question. I think you got the answer. You're just not articulating it to the point where the rest of the class can fully understand the impact. Why do you think we even offer CISP 440 at a community college? When it's a dead end, okay, there are no classes here that depends on CISP 440. But obviously, if it is offered, that implies that something depends on it, right? So what do you think depends on what we know as CISP 440 in the Los Rios district? It starts with a four-year university, okay? Because almost every single program in a four-year university has multiple classes that rely on what you are supposed to learn in CISP 440 here. So from that perspective, it is far from a dead end because you'll be definitely using what you learned in CISP 440 in a four-year university. I don't really care which CSU or which UC, they're going to have at least one class, possibly two classes, depending on those concepts. So that's why if you get a chance to practice, I would say take it, okay? It's a good opportunity to practice what you have learned if you have already taken CISP 440. For those of you who have not, by the time you take CISP 440, if you remember, you can get back to this note here and say, okay, now I should be able to figure this out. That's just another way to cross-reference content between classes. All right, but the bottom line is, yes, we can indeed replace the addition with a logical OR, which means the entire thing can now be computed using just logic gates. We got everything figured out at this point. All right, so let me give you a brief summary of how everything is arranged at this point. So we are given, we're given xi, yi, and also k0. So k0 is basically an input. That's what we are given with. Those are all binary digits, okay? Because we are now focusing on just base 2, calculations. So that's given. After that, we have q of I being r of xi, yi. So that definition has not changed. But this time, because of the specialization of base 2, we also know that this is now, I'm going to use my shorthand at this point. This is also known as not xi, yi, or xi not yi. Okay, that's my shortened notation. So in this context, the plus is no longer addition; it is a OR. And if you're wondering, Attack, when did you talk about this? I don't remember you talking about this at all in the class. It is in the module. I'm assuming you guys have read the module. And the notation of borrowing the plus symbol to also mean disjunction is in the notes, in the module. So let me show you what I mean by that. So I'm too lazy to actually look it up. So I'm looking up disjunction. And There we go. In this notation, I'm borrowing exclamation point x to mean the logical negation of x from C++ syntax. The plus symbol means disjunction, logical OR in Boolean algebra. So that is where these terms and notations are quote unquote hidden. I had no intention of hiding stuff. It is just that only in this context it makes sense to give you the definition or give you the idea that the plus symbol also means disjunction when the expression itself is Boolean. Are we good so far? So this means even if I don't say it in the lecture, you still have to read the modules carefully. Extract all the definitions, extract all the notations, put all of that stuff in one single place so you can reference all of that stuff easily. Do I sound like a broken record? I certainly hope so. Because if you recognize that, hey, Tech, you said that like just about half an hour ago, that means good, you are paying attention because now you're noticing that I have been repeating myself over and over and over again. On the other hand, for people who say, what did you just say? I'm starting to worry. Okay? So, and I mean that too. It sounds like I'm making a joke. I'm not. Because for people who do not recognize that I have been preaching the same thing over and over again, I really am starting to worry for those people. Anyway, so getting back to this part here. So we now know how to compute the Qs. And what else do we need to compute? The sum bits. The sum bits are pretty easy to do because it's kind of like the Q bits. It is the R between the Qi and the Ki, which now we know as, okay, it's the negation of Qi, Ki, or Q of I and not K of I. Okay, there we go. And I just need to look at, not a 1. It is supposed to be an exclamation point. There we go. All right, what else? The carry bits, okay? The carry bits is the messy one. It's definitely, the messy stuff, that we have to deal with. K of I plus 1, was known as the carry bit of xi, yi, plus, this is the actual plus, okay. Well, okay, it doesn't matter because we already know it's also the same as we can use an or in this case. So I'm just going to say the plus is meaning or in this case. So I'm going to emphasize that by changing it to an actual or operator. And if someone is asking me, so Tech, tell me when we start to introduce, the symbol, this is actually meaning or. Can someone answer that question? When was that symbol first introduced? Not during the lecture, but in the modules that I refer to in class. Which module starts to use this symbol to represent disjunction or?
This module, right? This module?
Well, it's actually the first one. Yeah, the first one that talked about the P and the 2 N transistors, that one actually introduced the wedge as AND, and then this one as OR, and then the cliff symbol as negation. So once again, that is what you're supposed to be able to do, is to read the module and be able to filter and to find all the definitions, all the notations, and then put it in one single place so that you can easily refer to all of those definitions. Okay? Just attending the lectures and taking notes during the lecture is insufficient for a class like this for most people. For some people, maybe it's okay, but for most people, it's not going to be sufficient. All right, so let's move on. So now we look at all of this stuff here, and this, by the way, simplifies to xi and yi, or qi and ki. We know it simplifies because we have now, we know that we can use conjunction to implement carry. So when you look at all of these definitions, they can all be done logic gates, which means, in theory, we should be able to create an adder at this point to add 2 base 2 numbers to the sum. Does that make sense to you? More or less? All right. So what we'll do I'll do one more thing, just so that we are clear on that concept. So this whole thing is really just, x of I exclusive OR with y of I. The symbol for exclusive OR is called O plus, in LaTeX, it is a plus with a circle around it. So that's the mathematical symbol of exclusive OR. And in this one, kind of the same thing, except it is QI exclusive OR with KI. All right? So are we good with, the circled plus is actually the symbol for exclusive OR. All right, excellent. All right, so now, based on all of this stuff here, we notice certain structures, okay? Because we notice that the way we compute Qi from Xi, Yi is exactly the same way that we compute Si from Qi, Ki. And also we notice that we need to compute the carry or the possible carry contributed by Xi plus Yi, with this term. And we also have a similar structure for Qi, Ki. So that means, if I were to implement this circuit, maybe I can use certain structures. So this way I can just basically create smaller structures and then create larger structures based on the smaller structures and then stamp out all of these things. So things are much more organized, it's easier to look at, and it gets the job done in a neat way. Okay? So what I'm going to do is I'm going to say, okay, let's go ahead and make a device that can compute both the exclusive OR between these two, and also to compute the conjunction between the same two bits, in one single device, because we know that we need that in order to compute the sum in base 2. So this is where we're going to start with Logisim, and I'm just trying to see if I still have one up. Nope, I do not. That's okay. We'll go ahead and start up Logisim. And just looking for, okay, maybe I'll just use this one. So java-jar, and then we go to the downloads folder. It's called Logisim310.jar. And it's going to start in the wrong terminal or the wrong screen. That's okay. Just have to move it here. There we go. So the first thing I'm going to do is to make my exclusive OR. Now, you don't have to do that, because if you look under gates, there is exclusive OR right here. Okay, but assuming that we don't, okay, I can always make my own. So to make an exclusive OR, I need 2 inputs. I'm going to need one single output as the exclusive OR output. I will need 2 AND gates, but the AND gates do not need to be this wide, so go for narrow. It only has 2 inputs. So duplicate that. And I would also need an OR gate, to combine the 2 output from the AND gates. So once again, we can use a narrow form and reduce the number of pins to 2. All right. So now we got the basic stuff here. Now with the AND gate, you notice that you can negate the inputs individually. So that's what we're going to do. So with the first one, I negate the first input. And then with the second one, I would negate the second input. So this way, I'm not going to need actual extra gates to do the negation, because the negation is attached to the input of the AND gates already. So this goes in here, and it also goes in here. This one goes to here, and it also goes to, and it also goes to here. And then the output of the first AND gate goes to one of the inputs of the OR gate. The output of the second AND gate goes to the other input of the OR gate. And then they both feed to the output. So here we have our exclusive OR. So we'll just kind of briefly test to make sure that it works. Yes?
How do you do that negation thing on the 2?
The bubble thingy?
Yeah, the bubble thingy.
Yeah, so with the bubble thingy, this is where you do it. You can negate, one or both or neither of the input pins. So it is negate 1, negate 2, and it gives you the position of the pin or the input port that you're negating. And the bubble means negation. All right, so here's the first thing, okay? This circuit is representing exclusive OR. So if I were to comment or to give the pins a name, okay, this pin, oops, this pin, if I call this pin F, no, there we go. If I were to call this pin F and call this pin G, because I don't want to call these X and Y because this is generic, this pin would have been F exclusive OR with G. Oops, G, not J. There we go. So one thing you might want to do, in your spare time, not spare time, but in your study time, after the lecture, you might want to look at this and try to figure out why it is actually doing F exclusive or G. Okay, especially if it doesn't seem obvious to you, you might want to kind of follow this logic and figure out for yourself that it is actually doing the same thing. So now I'm going to change the name of this circuit. So we'll go ahead and change main to exclusive OR. Even though we do have exclusive OR as a gate in Logisim, hey, it doesn't hurt to make this one ourselves. So edit circuit appearance, and I'm just going to label exclusive OR, so this way I don't forget what this is about. So here we go. So now I got my exclusive OR. The next thing I'm going to create is called a half adder. So HA for half adder. So the half adder, let me show you what I mean by using the half adder, what it is actually trying to represent. So the half adder is on one side, trying to compute the R of 2 bits, and at the same time is trying to compute the AND of the same 2 bits. Because we have two things that are very common, that has the same structure. So if I make a half adder, I can now stamp it out, and simplify the appearance of the circuit. So going back to Logisim, we have 2 input pins. Once again, we can call these F and G. So we'll go ahead and name one F, and then name the other one G. Oops, G, there we go. And then we want 2 outputs out of this thing. The first one is R of FG, and then the second one is C of FG. But this is all in using base 2, so we know the C of FG is really just the conjunction of the 2, and then the R of FG is really just the exclusive OR of the same 2 pins. So I'm going to use the exclusive OR that I just made earlier to handle the exclusive OR, and we'll pull a regular AND gate for the C of FG. So once again, just kind of go through the tedious process to make it look a little bit nicer, like so. And now we just have to do the wiring. So F goes into the exclusive OR, F also needs to go into the conjunction. G, kind of the same thing, has to go into both gates, like so. And then the output of the exclusive OR becomes the R of FG, and then the output of the AND becomes C of FG. All right, so are we doing okay so far with this circuit here? The reason why this makes sense is because, with respect to xi, yi, I need xi exclusive with yi to compute the q of I. With respect to the computation of k of I plus 1, I also need to compute the c of xi, yi as one part of the overall thing. And then on the other side, in order to compute the sum of, for a particular position, I need to get the exclusive OR between the qi and the ki. But those 2 bits, qi, ki, are also used to compute as one of the components of k of I plus 1. So that's why this makes sense, because it represents the kind of computation that we need to perform for xi, yi for one thing, and also for qi, ki for the other part. So that's why it makes sense to have a half adder like this. And then we are going to change the appearance just so that I don't forget which pin is which pin. The input pins are not too big of a deal, so I'm just going to label, I'll go ahead and label those 2 too. So we got F G, and then the output is more important because one is the R, and then the other one is the C of those. So I'm going to move things around a little bit just so that it looks a little bit nicer. So F goes here, G goes here, and then R of FG goes here, and then C of FG goes here. I mean, this is kind of like, documentation, right? If you don't do it, doesn't mean that, it won't function. It just means that when you look at the overall circuit, you might scratch your head, a week from now and go like, what is that? What is that pin? So now I'm pretty sure I won't get confused about, these pins. And I'm even going to label the overall design and say, this is a half adder. Okay, so there's no confusion whatsoever what this thing is if I just look at a circuit that is making use of this, particular subcircuit. All right, well, if one thing is called a half adder, does that suggest to you that there will be another thing, a full adder? Very good. Okay, so this is the kind of thing that I would expect all of you to do, is to say, hey, if there's a half something, there has to got to be a full something or something, along that line. So that's what we'll do next. So we go to project, add another circuit. This time we call that a full adder. All right. Just from the name of full adder versus half adder, do you think the full adder is going to make use of the half adder? And if so, how many of them? And there we go. Excellent. So we're going to slap two of these things into the full adder circuit just because of the naming of the circuit. Okay? But what it's doing, I need to explain. So let me go back to the Joplin first. So what we're trying to do is the full adder is going to handle one column of the entire addition. Okay? So one full adder handles the entire full column of the adder. So that would need 3 inputs and 2 outputs. So I'm going to slap those things here first, and then we'll talk about what those things are. And then we'll try to figure out, what to do with the wiring. So I'm slapping these, pins in first. All right. So one of the input, I'm just going to call this Xi, and I will call this one Yi. And the output, I will call this one Si, and I will call this one as a K of I plus 1. And this is going to be Ki. All right. So given that we are starting with, we are given Xi, Yi, and Ki, and we need to compute Si and K of I plus 1, how am I going to wire up this whole thing? Okay. So we'll start with Xi. Okay. Where do you think Xi should go? I mean, the two half adders are symmetric, so we'll just use up the top one first. So where do you think Xi should go to? Because addition is symmetric, it can go into one of those two, but which two are we talking about?
Sorry, I got lost around the half adder.
Okay, so we want to figure out how to compute S of I. So do you remember what is S of I? Okay, let's go back to the definition, right? So S of I is Qi exclusive OR with Ki. Then you go back to this diagram here, you go like, but heck, where's Qi? So now you go like, darn it, we don't have Qi here because Qi is not an input. Qi is what? Look at the definitions again. Where's Qi? Qi is the exclusive OR between Xi and Yi. All right? Are we good so far? So now, if I go to this diagram here, and what the output pins of the half adders are doing, so how should I wire up the first or the top half adder so that I end up with Q of I? Exclusive OR, which is the R of FG, right? So if okay, let me do this wiring first, and then you guys can tell me whether that's going to work or not. So if I hook this XI to F and hook up this one to G, am I going to get Q of I as one of the outputs?
Yes, in RMFG.
This is my Q of I, right? And where do you think this should go? Because eventually I want to compute S of I. Q of I is just an intermediate term, so I can refer to it. So this becomes one of the inputs. Yeah, this is going to look bad because of running into the label. So it's going to run into this one here. And then this one here, K of I, which is one input, goes to the other input of the other half adder. So given this is the diagram, how should I wire up S of I? Where should it go? Well, let's go back and take a look at what is S of I. S of I is the exclusive OR between Q of I and K of I. I got Q of I as one of the outputs of the top half adder, right? So what I need to do is, to take this one and hook it up to S of I. And then this one here, C of FG, is just going to be, well, okay, this is really kind of interesting because if you think about it, we have two output pins, one here and one here that are not connected to anything, and then we have a single output pin here, which means more likely than not, we need a way to combine those two. So tell me again, what exactly is this pin or this port doing here? It is the C of FG, but F and G are just referring to the names of the input ports. What the way it's connected now is this is actually C of XIYI. Yes? No?
Yeah.
Maybe?
Yeah.
Yeah? Okay.
Yes.
Because of the way I hook up the input pins into the half adders. So what about the other one? What about this one here? This is the C of
Q and KI.
QI and KI, right? Very good. So now we go back to the equations and we look at K of I plus 1. Oh, it is the C of XIYI or the C of QIKI. Okay, switching back to here. Now we can see that this is C of XIYI. This, on the other hand, is C of QIKI. So what do I need to do to come up with K of I plus 1? This thing here, or this thing here? What is that? It's an OR. Very good. Okay, so we need an OR. So we get the OR gate here. Once again, tediously change it back to the usual format that I need the gates to be. Put it here. Slap this output to here. Slap this one to here. And the final connection. There we go. All right, so I'm going to give you guys some time to kind of look at this and also look at the equations at the same time. Okay, I'm not really sure how that can be done easily. So we are looking at this, these three equations, and we are looking at this part here. Let me see if I can do this, because if I can, oh, that doesn't work. Because it's optimized, it's maximized here. So if I try to resize it, it doesn't like to do that. I have to do everything manually. I think we can do it. We can do this. There we go. We got everything on the screen. So can we see how the three bullet points, in terms of equations, are implemented by the Logisim circuit at this point? Yep.
Yeah, I get, like, it actually is making, like, more sense to me right now. I just want to clarify.
Mm-hmm.
Just kind of, can you redefine what QI or exactly was?
If I want to label Q of I, it is basically this wire. This Y
Yeah.
here is, Q of I.
Okay.
So we can go ahead and label it. I mean, that's, pretty easy to do. So we'll go ahead and label it. And that's just using the text tool. There's no easy way to label just a wire. So this is basically just Q of I. All right. Okay. As you're pondering on this, diagram, I'm gonna set up the row taking. So, and I don't want to disturb this, which is kind of, I can do this, it's just that I have to drag one of these windows, to my other screen, and then show you exactly what we were showing earlier, which is this and Joplin in the reverse order. There we go. So now I can do stuff on the other side without disturbing you guys looking at these two, looking at the diagram and the equations. Yes?
You were going really fast. Well, for me.
Mm-hmm.
When you were doing the half side, the exclusive or
Excellent.
also show that on the screen.
You want me to show the half adder? So that's how the half adder is done. It really literally is just taking the both inputs and making an exclusive OR out of the two inputs with one of the output pins, and then make a conjunction out of the two input pins with the other output pin.
Okay, and then can you show
How do you do
the
that?
exclusive one?
Can I show you
The exclusive or.
the exclusive OR?
Okay, can you explain the double thing again?
It's a negation. Yeah.
And how did you get it?
I got it out of changing the negate one. You turn it into a yes. So each input port of an AND gate or any gate can be individually negated. All right, so let me go back to the full adder. So this way you can look at this diagram, look at the equations when I'm setting up your row taking activity.
I'm gonna have to go back to the lecture later and see how to make the half adder, because I was lost around there. I had a second where
I see.
couldn't save the XOR.
Oh, okay,
So I had to go copy paste everything to a different one from the main.
I see.
Can you show like the files and the pictures?
Or there's like, can you look like the Joplin folder onto like Google Drive or something?
Yeah, the Joplin is easy. I can send you guys the actual Markdown file. So that way you can install Joplin on your own computer if you want to, and then just export it to whatever format you want. The nice thing about giving you the actual Markdown file is you can now jot down your comments, whatever you're thinking, into the same document. So let me finish setting up your row taking activity. I will give you guys up to 10. So 10 minutes should be more than enough to get this done. Save and publish. And I'll just go ahead and show you the row taking activity. So this is the row taking activity. It's named after today's date, which is 2022-0901. And then the answer to the question is carry. Not surprisingly, right? This is not. So CARRY, all lowercase, is the row taking word for today's row taking activity. And you have up to 10, to get this done. I think that should be more than sufficient time. Well, the point of the half adder, because getting back to the half adder, because that seems to be a point of confusion. So the idea of the half adder is just so that we don't have to put in like an exclusive OR gate here, and then a conjunction gate here, another exclusive OR gate here, and another conjunction gate here. It's just to reduce the complexity of the full adder diagram. That's all it's trying to do.
No, I know, I just didn't see it because I was constantly trying to figure out how to do the saving thing.
Ah, okay.
By the time I figured fixed it. I saw it go instead of the half adder and it was moved on to the full adder and I'm like, oh, dang it. I guess I'll have to do this later.
Yep. Yeah, focus on the concept, during class, because trying to follow is going to be a little bit harder because I have worked with Logisim for many years. So the pace is going to be a little bit hard to follow.
It's like right now I can see the symbols. I
Mhm.
can like make deductions like, oh, if R of FG, that means it's R of XI and YI or whatever. I can do that. It's
Mhm.
just it's not friendly in here yet.
Right.
So I'm like, it's not really clicking for me yet.
Okay. Yeah, I think it would click, when you start to construct it, it will start to click a little bit more. And you constantly have to make a reference back to the actual definition of the bits, because that is what is driving the design. This design here, the Logisim implementation, is really just a diagram version of the text version of this. So it has the same structure, it's just that it's in the circuit.
And I'm only barely following along with the text definition.
Oh.
So
I see. That's why for each hour of in lecture time, you have to schedule up to 2 hours of outside of lecture time to kind of digest the concepts. All right, so are we ready to move on? Have you guys all participated in the road-taking activity? Yes. Okay, excellent. So we are moving on, and what we're going to do next is going to be utilizing the full adder to actually make a 3x3 adder. In other words, the input numbers would be a 3-bit X, a 3-bit Y, and we'll come up with a 3-bit sum, and then we also come up with K3 as an extra output bin. All right, so talking is hard, because it's hard to kind of tell you guys what it's supposed to do. So I'm just going to say this is a 3x3-bit adder, but using carry ripple. Okay, that's the most important part to remember is this is using carry ripple. All right, so we're going to slap a few things into this diagram. The first one would be X, and because X is 3-bit wide, this is a multi-bit input pin, and I'm going to do a duplicate of this, so it becomes Y. And then K0 is also a given, so that means it is its own input pin. So it's a single bit input pin called K0. Whoops, K0. There we go. On the output side, we have sum, which is 3-bit wide. So here is sum, and it is 3-bit wide. And then we also have one extra pin, which is K3. There we go. So from the perspective of writing code in C and C++, I have just defined all the parameters to a subroutine. Okay, we got 3 inputs, 2 outputs. Now we need to figure out how to get it done. Question?
No.
Okay. Now each full adder can handle 1 column in the addition. Since we have 3 bits, kind of makes sense that we need 3 of these guys, right? 3 of the full adders. So we'll slap 3 full adders here. I forgot to label the full adders. So now I cannot remember which pin is which pin, which port is which port. And the nice thing is you can always go back and change it if you want to do something like that. So the first one is XI, YI, and then we got XI, YI, and then KI. And then on the other side, we have SI as one of the outputs and K of I plus 1 as one of the outputs. So now I just have to move these things around. Okay, XI. I'm pretty sure if I do this in China, I'll be in big trouble. Do you guys? If I label these pins, and I'm actually living in China, I might get myself into trouble. What is the last name of the Prime Minister of China?
Oh yeah,
xi, right? C. Yep.
Oh.
At least it's not Pooh Bear. I mean, all right. So now we get back to the 3x3 adder, and you can see how all the labels are retroactively put into the design. All right. So it looks kind of makes sense that I can do something like this, right? Except it does not. Why is it not working? Damn it.
Because the XI and the full adders are only 1 bit.
Exactly. So the full adders are having input ports that are only 1 bit wide, but the input pin is 3 bit wide. So what do we need? Splitters. Okay, so there's a reason why I emphasized the use of splitters in all the previous labs, because now you guys go like, oh yeah, easy peasy, man. You just get a splitter or get a few splitters and we are done here. So we'll go ahead and pick out the splitter, except how do we configure the splitter in terms of a fan out?
3 bits in, 3 bits fan out.
Yep, 3 bits wide and 3 bit fan out of 3. So now we take out each individual bit out of X. Very good. And we need to do the same thing with Y. So duplicate, do it with Y. And it's not YY, it's just Y. There we go. And we need one more for the sum, because each full adder is only contributing 1 bit for the sum. So in this case, I need to flip it and just make it face the other way, which is west. There we go. Okay, very good.
And then I think we can just connect the dots, right?
Yep, we just connect x0 to the first full adder, connect y0 also to yi of the first full adder. And then because this is responsible for column 0, so this is the only one that makes use of k of 0 as k of I, because in this case, for this guy, I equals to 0. Okay?
I got this one.
Hmm?
I got this one, I think.
Okay. So
Oh,
I'm
wrong now.
So I'm gonna say I equals to 0 for this one. Oh, that's not a good place to put it. So I'm just gonna not do it. Okay, so next, what about this guy here? This is responsible for bit 1. So we have x1, y1, and k1. Hold on a second, there's no k1? Well, how are we gonna deal with this? There's no k1. Yep,
We can use ki plus 1 from the previous one.
exactly, because I equals to 0 for this particular full adder, which means k of I plus 1 is literally k1. So k1 goes to k1 over here. Okay. Oh, I did not leave enough space. I did, but it's not nice. Sorry.
It's a nice little fractal pattern it's got there.
I used to do a board layout. So with board layout, you kind of have to figure out how to route a wire without overlapping with another wire. It's really fun. It's like solving a puzzle.
This is probably causing me pain.
This is not too bad because you can actually have stuff kind of flying over.
Yeah.
Yeah, but on a real circuit, like a printed circuit board, you cannot have things flying, quote unquote, flying over. Now, if you can pay for the expenses, you can have a multi-layer board. But if not, you have a 2-layer board: top layer, bottom layer. Yep. But it's a lot of fun too. I mean, I have to admit, it is a lot of fun to do that too. All right, so this is x2, it goes to column 2. This is y2, same thing, it goes to column 2. And, oh, by the way, let's handle the k first. So for this particular full adder, it is responsible for when I equals to 1, which means k of I plus 1 is k2. So k2 goes into the input of k2 of the next full adder, like so. And because this is, for this particular adder, I equals to 2, and so k of I plus 1 is literally k3. So this one goes straight to one of the output pins. just like that. So the only thing left to do is for me to handle all the sum pins. So this is when I equals to 0. This is S of 0. So it simply goes to bit 0 of the sum. This is S of 1. There we go. And this is S of 2. Woohoo! We are all done.
This one was just kind of plug and play.
Yeah, it is. I mean, it's once you have the full adders, things are easy to route. But if you try to make this entire thing, what we see here, using just individual AND gates and OR gates and NOT gates and exclusive OR gates, it's going to be busy. Okay? Can you do it? Yes. But would I recommend doing it that way? No. Okay? It's just like, when you don't want to write a subroutine in C or C++ that has 500 lines. Yep.
I see what you're coming from, because like doing it with just the transistors would be like coding in binary, right?
Yep.
And then doing it like this would be like a coding in assembly.
It's structured programming. It's just like, in a C or C++ class, why do you have functions? Why do you have subroutines? Because you want to organize things and you can reuse code. This is the same thing. We are trying to reuse code as much as possible. All right, so now it's time to test it. So let's test it with something that's easy, like 5 plus 2. All right, so 5 plus 2 is pretty easy to do. 1, 0, 1 is 5, 1, 0 is 2, and then the output is 1, 1, 1, which is 7, because it's 1 plus 2 plus 4. That works out. Nice. What about 3 plus 2? Okay, this is 3 because 1, 1 is 3, 1, 0 is 2, and the output is 1, 0, 1, which is 5. That works out too. Okay, so just by testing 2 individual cases, it seems to be working. Let's work on one that doesn't seem to make sense. Okay, so let's try to add 7 because 1 plus 2 plus 4 is 7, and this is 2. 7 plus 2 is 9, and the output is just 1. It's like, doesn't make sense, right? Until you look at K3, because K3 says there's an overall carry of this entire operation. That K3 is basically saying, I can't really put it into the sum, but guess what? There's a leftover quantity of 8, which is 2 to the power 3, that also is part of the answer. So it does make sense that you have 8, which is represented by K3 being a 1, plus 0, 0, 1, which is representing the value of just 1. So it's still representing the result of 9 in a very strange way. Are we good? Question?
No question. And then I think you can also like expand it, so you can like add 4 bits.
Yeah. So
just by adding the different amounts of bits, bigger splitters and more full adders.
If you want 4 bits, you just need one of these, one more of the full adders. The splitter needs to split one more. You extract bit 3 to go here, and then the output of k plus 1 here just goes to ki of the next one, and then the k of I plus 1 of the next one goes to k4, which is also just an output pin. And also, you have to extend the sum also by 1 bit. So, and I'm going to say, you might think this is the end of that entire module. Yay, we can get to the weekend without having to worry about new stuff. No, that is not the case. Every time you think, this has to be it, right? We are all done here. So what we have done up to this point is exercise 5.1, implementing a 3-by-3-bit binary adder using AND or NOT gate in Logisim, And then, but wait, there's more, okay? So I still need to explain why there is more, okay? Because there's a problem with this particular design. So with this design, you can see how, K1 is utilized by this full adder in order to come up with K2, and K2 is needed in order to come up with K3. So there's a daisy chain dependency. Until the first full adder is all done, and this particular wire has the right answer, the second full adder cannot really give you the right answer. Will it give you an answer? Yes. Would that be the right answer? Maybe. So there's a linear dependency. If you are to compare the timing or how much time it takes for a 64-bit adder compared to a 4-bit adder, the 64-bit adder is going to need 16 times the amount of time for a 4-bit adder to come up with the right answer. Because it's linear, there's a linear dependency. So it doesn't sound too bad, right? It does not sound too bad. But if I tell you there's a faster way to do this, okay? And let's just say that Intel, thinks, oh, this is the way to do it because it's simple, it's scalable, it's all, it's all good. And then AMD said, I found a better way to do this. It's constant time, okay? The amount of time it takes for a 4-bit adder to come up with the right answer is the same as the 64-bit adder. It is like super fast, okay? Do you think Intel would go for this is what we call a carry ripple adder, because the carry is being rippled from one full adder to the next, and then it ripples from the next one to yet the next one, and so on. This is called the carry ripple adder. It is slow. So that means, if we have a faster way to do this, we want to use the faster way. Does that make sense? So I cannot get into the full detail, of what the faster way really is, because that's what section 6 of the notes is about. But wait, there's more. Okay. This is where things really kind of go a little bit more complex. This proof I don't need you to understand. You just have to go like, okay, so k of I plus 1 starts with this, and eventually it boils down to this. Okay, you can kind of not fully understand what is going on in between, just kind of go from here all the way to here. And then we're using substitution. We can finally derive K1, which is like this, K2, which is like this, and then K3, which is like this. Okay, and then I claim the logic circuit for K1, K2, and K3 will take the same amount of time to compute. But you guys looking at these three equations, this one, and this one over here, you go like, oh no, that cannot be the case, right? Because K3 is obviously a lot more complex with more terms compared to K2, and K2 is more complex than K1. But you're forgetting one thing if that is what you're thinking, because you're forgetting that while P1, G2 is being computed by a single AND gate, another AND gate with 3 inputs can also be computing P1, P2, P1, G0 at the same time. And at the same time, another AND gate with 4 inputs can compute P2 and P1 and P0 and K0. So that means we can have 3 AND gates happening at exactly the same time. They would all come up with the answer at also exactly the same time. Then we feed 4 inputs into one final OR gate to get to K3. In other words, when you look at the structure and try to maximize operations in parallel, the amount of time it takes for K3 to be computed is the same as K2, and it's also the same as K1. That is the trick. So the question is, how do we get to this kind of complex equation that gives us structurally the same level of logic gates, even though at each level they can have different complexity. So that's one. And then we'll also be looking at this notation here. I will explain the notation, but for the most part, it is kind of the equivalence of sigma notation, except we are not adding, we are ORing, and we are ANDing multiple terms. That's it, okay? It is still a for loop of some kind, except instead of adding, which is what the sigma notation is trying to express, this one is just doing logical AND and logical OR, but in the same fashion. You specify where it starts, you specify where it ends, and then all the terms in between will just be all ANDed together or all ORed together. I will explain all of that next Tuesday, but you really need to read ahead of time, because if you don't, the notation alone, is going to be a problem. It's going to present an obstacle to your understanding during the lecture. All right. Any questions about today's lecture? All right. So I do have to emphasize, I know I'm being dad, I'm getting into dad mode here, starting to nag, people. The concepts they have a linear dependency as well. So that means, not being familiar with the concepts, notations, and definitions that have been introduced up to this point is going to make future topics really hard to get. So that means, when you have a long weekend, like this weekend here, I strongly suggest people to kind of make sure that all the topics, all the concepts that have been discussed, they're cleared, okay? So that you're ready for next Tuesday when we start on something like this. All right, so you guys can go ahead and take a 10-minute break. I'm going to go set up the lab for today. It should not be a long lab, maybe half an hour or so. So that will conclude our class time today is the lab. But come back here in about 10 minutes. I'll have the lab ready. I will stop the recorder for now.